Grazie. Buongiorno, signori, signora. Let me now switch to English because I'm slightly better in that language than I am in Italian. And let me first say it is a great pleasure to be in Fuori di Sopra at this meeting, Italian Fracture Group. And I thank Professor Ferro and Professor Lupu very much for inviting me along, Professor Sutherland and Professor Ferro. I have a talk for you that hopefully you'll find interesting. It's trying to address the question I raised yesterday to Luca about in structures, in particularly steel and in structures, we have a lot of continuum mechanics solutions for predicting the fatigue life, which all work to a greater or lesser extent. And for some time it seemed to me that one of the reasons they don't work better than they might, and therefore allow us to use materials more close to their particular fatigue strength parameters, is that we don't really understand the material aspects of the influences on fatigue. And particularly in the case of welds, you have microstructural influences and heat input influences, and they lead to microhardness gradients and to residual stress gradients. And so in this I've had a go at characterizing the residual stress and microhardness gradients for a variety of welds to see whether one might be able to predict from some aspects of the microhardness and the residual strain the fatigue range of a variety of welds. It turns out that you probably can, but probably my data set is not big enough. One of the difficulties of advancing fatigue life prediction is that you require large matrices of experiments, which in a particular case, residual stress measurements, tends to be very expensive. And therefore we often don't get all the data we like. So my colleagues with this work, by the way, just to prove I do have an Italian connection, is Matteo Bosi, who very kindly is in the audience today and was an undergraduate student at the Università di Ferrara. And you'll see that I am actually associated with Ferrara as well. And a PhD student, Si-Pin Ting, and two colleagues in South Africa who assisted me with residual strain measurements. So what have I done? Well, we've had a look at parameters that might be used to predict the fatigue ranking of fusion welded high-strength steels. And the background of this work was that Corus, the steel maker in the UK, now part of Tata Steel, had done some work on high-strength steels and had found contradictory results for fatigue performance in terms of what they thought the residual stresses did. And they were interested in doing some residual stress measurements in these steels. And so I came along and persuaded them to fund a PhD project. And it turned out that the residual stress measurements they made using hole drilling and surface X-ray were not explaining the fatigue data at all. And so we're interested really, or I'm interested in understanding process property performance relationships. In other words, in welding, you've got process inputs, you use a filler metal, you use some heat, and you get a variety of induced properties. You have residual strain, you've got dilution of the alloy in the fusion zone, you have a variable microstructure and a variable hardness. And that makes it quite difficult actually to predict performance more precisely. But what you tend to get is reduced fatigue life, large data scatter and poor predictive capability. And so if we're going to advance that particular aspect there, it means we do have to take some account of what welding is doing to the microstructure. And in principle, at a first order, if one understood what residual stresses and microstructural changes did to welds, you might be able to provide some advice to fabricators. And this is actually quite useful advice if you can get around to it. Should they make welds with undermatched, matched, or overmatched filler metal to get particular properties? Should they use higher heat input with fewer weld passes or lower heat input with more weld passes? And if you could even get that far, it would be quite beneficial. And because you find that, although this isn't taken account of in the fatigue design codes for welds, you often find there's a crossover in performance for two welds, nominally similar. And so it's worthwhile assessing life at shorter life, about 10 to the 5 cycles, and at lives longer than 2 by 10 to the 6. And you have another difficulty, of course, with longer lives in doing all the experiments that will establish the long life region adequately. Everything has a cost, as Maurice Sonsino noted yesterday, and these costs are just too high often for relatively small research projects. So this is a roller quenched and tempered steel. It's a high strength steel. It's called a 701 normally because it has about a 700 megapascal yield strength. And I used, or Chorus supplied, plates 8mm and 12mm thick, and we welded together two plates a meter long by about 150mm wide using MIG welding. And these plates have slightly different properties, but they are actually significantly higher in yield stress than the stated 700. So you're up around 800 megapascal yield as manufactured. So these are actually high-strength steels. And we used 3 filler metals, nominally corresponding to overmatched, matched, and undermatched in the properties, tensile properties of the actual filler metal themselves. You can see that the overmatched has a 980 yield stress as against the sort of 800 of the roller quenched and tempered steel. This is close at 700 and that is low at 500. We use 2 values of heat input, and those lie within the envelope stipulated by a British standard for offshore use. And so I've got a fairly broad experimental matrix to try, which should in principle give quite variable micro-hardness and residual strain grade, and does. And so if you found a reasonable correlation across that broad range of data, you might think that you were on the right track. So when they made the welds, this is what they did. This is 1 kilojoule per millimeter, 8mm plate, 3 passes. 1 kilojoule 12mm plate, they're using 7 passes. 3 kilojoules, 8 plate, 2, and in that 3. So we've got a matrix with 6 different weld conditions for each of the 2 thicknesses. And as I say, that does tend to give you a good variation in hardness, residual strain, and fatigue performance. And so if you can find some way of predicting the fatigue ranking, there is a sporting chance that you're getting something true. So what do we do with all of this? And I must say this project has taken me quite a long time to achieve. I mean, it's probably been going around for about 5 or 6 years as I steadily ironed out each of the wrinkles. In particular, the residual strain measurements are complex, as you'll see, expensive, and require you to put forward experiments to the Central Europe, well, the European facility. You have to be careful when you say Central European. They are the Central European, but it's for the whole of the EU. Central to the EU, not to Central Europe. So that is the IL and ESRF in Grenoble. So I wanted to measure the residual strain profile transverse to the weld on lines 1mm below the toe and at mid-depth. 1mm below the toe is probably where you've got undercut intrusions and you would expect crack initiation to be occurring, or at least cracks to start growing. So that residual strain and the hardness there might indicate an effect on early crack growth. The mid-depth one I'm sort of assuming dominates the longer crack lengths, and I was interested to see which one might work the best. So I measured residual strain along those lines and micro-hardness profile along the same lines. I would have liked to have done a full 3D residual strain measurement and get the residual stress directly from that, but unfortunately that is just too expensive. You will not get the beam time at European facilities to do that. This took about maybe 10 days of beam time on neutron diffraction, and I guess you are never going to get 30, 40 days for something straightforward in their view, like measuring residual stresses. So what we've then done is we've had a look at the fatigue performance, and we've only used 3 ways of doing this. Nominal stress, which I didn't expect to work very well and didn't, but hey, it's there, we do it. And we had a look at hotspot strain and hotspot stress, in other words, the structural stresses at the weld toe. And it turns out here that the actual hotspot strain, which is what you might expect, does a better job of correlations, but you don't a priori know that, so it's worth having a look. And what I was interested in, as I say, is the fatigue ranking of the welds relatively at lives of 100,000 cycles per million. And I'm trying to eventually find relationships between turning points in strain and hardness profiles and the microstructure, and somehow use that information to predict the fatigue ranking. So, summary of what I've said already. I'm interested to see whether some combination of residual strain and hardness information can predict the observed fatigue ranking, using things like turning point magnitudes, the range of strain and hardness excursions, gradients and their change across the weld toe, and the yield strength of the weld metal. But like many things in life, if you're in Korea or you're prepared to buy the equipment, you can get a map of yield strength across the weld matrix from micro hardness measurements, but sadly I don't have that, so we end up always doing a little bit of the whole story. And this is what I want to do. I would like to gain insight into factors underlying the variability of fatigue performance in high-strength steel welds. And one of the things that Corus had shown originally in previous work was that if you had the same welds fabricated by 2 or 3 people and then stress relieved as well, some of them, you ended up with completely different sets of fatigue data. And it got worse as the strength of steel went up. And so they were said, we don't really know what this is. We've done some residual stress measurements. They didn't explain this at all. They gave a counter result. And at this point I came along and said, in exchange for only a small sum of money, we can run a PhD project. This is it. So we get these plates. These are 1 meter long by now 300 millimeters wide, and we cut them up. And again, there's always approximations to what you can do. You need a fairly big specimen to be reasonably certain that you've captured the residual strain field that is representative of the full-size plate. And so that is the residual strain specimen there. It would be nice to test fatigue specimens of the same width, but unfortunately the testing machine won't do that. So then you figure that, well, if I keep these as 40 wide and don't change the length there, there's a sporting chance that the transverse residual strain in that direction is moderately untouched, and with any luck that will be the strain that will matter more to the weld rather than the sum of the principal strains, but you don't know the answer. So these are fatigue specimens, and that one there was used for microstructural analysis, as you might say. So properties of interest are the hardness of the microstructure, yield strength of weld metal. They're both highly variable across the weld zone, and it's only possible with the equipment we've got to measure tensile data in the middle of the fusion zone, and you can do that with a 2.5 millimeter diameter wasted specimen. And then you can have a go at correlating the actual data with indicative filler metal properties. Just have a look at the accuracy of that tag of overmatched, matched, and undermatched filler metal. It turns out that that is not necessarily super close. So this table gives the tensile results. This is the weld process conditions, heat input, filler metal type, undermatched, matched, overmatched, plate thickness. We measured 0.1% proof strength and tensile strength. This colour here, I'm not very good with colours, I'm afraid. I just choose them. I can't describe them. That colour there is undermatched, the yellow is matched, and what I think is blue is overmatched. And it shows you here the original strength of those filler metals, and there the strength of the plates. And you can then correlate those strengths with these values and those values. So if you have a look at undermatched filler metal, you do a reasonably good job. So if you think you've made an undermatched weld, you have. Both the proof and tensile strengths are undermatched in all the cases we've looked at. If you look at matched filler metal, you get an undermatched proof strength in all cases, but more or less a matched tensile strength, about 5%. And so the concept of talking about welds as matched, undermatched, or overmatched is a little loose. And if you use the overmatched filler metal, you get undermatched proof strength in certain cases, and though these is overmatched 8 thick, low heat input, overmatched 8 thick, high heat input, that's the abbreviation system used. You get an overmatched proof strength in that one, and an, I guess random around in all the others, and an overmatched tensile strength except for that one, which is matched. So as you steadily increase the strength of filler metal, it becomes more difficult to actually predict what the weld property is going to be, at least in this high strength steel. And another set of generalizations you can draw out is that The lower heat input generally gives proof strength values close to the desired level. They're also invariably higher than the proof strength values obtained at 3 kilojoules, which is a reasonable conclusion. You would expect that. But the tensile strength is more variable. And there are certain cases where the higher heat input gives you a higher tensile strength than you get with 1 kilojoule per millimeter. And so the supposition is your data is influenced by fusion zone size, which is a function of heat input and plate thickness, dilution effects, and the number of runs, and it is going to be quite complex to actually predict what you do get, except the undermatch does seem to work fairly well. Well, my take on this work was then that the microhardness could be used to characterize the effect of heat input and heat flow on microstructure across the weld zone. We made automated microhardness measurements. We've smoothed the data. We've looked, say, at lines 1 millimeter below the plate surface and on the midsection plane, on the assumption that those might be true, and I'm interested to know which dominates fatigue performance. Now, the sort of data you get out of this is this, and you can see that it is actually quite variable from weld to weld. This is undermatch 12 high, 1 millimeter depth, that's at the mid-profile, so that white line there tells you where the measurements have been made, and this is the profile along that line of hardness. And so they are quite variable from weld to weld. So as I say, if you've got these sensors at all at the end of the day, you should be picking up something that is true. So you can say that you do get large gradients with the weld tone. My assumption in this work is that it is the gradients around the weld toe position, because that is where these cracks are going to start, that are the key defining influences on fatigue in some way. And this just shows you a different one. This is undermatched 8H, high input, at, again, 1 millimeter mid-depth. And the turning points you can relate fairly well to interpass, fusion zone, and heat affected zone boundaries. And just to indicate that there are substantial differences, this is typical data for a matched 8H, which is those two there, and an overmatched 8L, which is that data there. So there are big differences. Right, so now what I've got is I've got the microhardness data more or less sorted out. Now I need to get the residual strain data sorted out. So we did neutron diffraction strain scanning on full width specimens containing 150 millimeters of weld run, on the assumption they should be representative, and we've measured transverse strains across the midpoint of the weld. And again, we've measured along the same sorts of lines, obviously not to scale, but it's indicative. We've measured a matrix of points from minus 30 millimeters up to about plus 60. And we've done that using the SALSA instrument at Grenoble, another fine alpine site. It's a vague picture of the badly overexposed of the Alps in the background, close to the nuclear reactor. And this is the hexapod table for the SALSA instrument with one of the weld plates in position, and you can measure the strains. And the point about this is you can measure strains actually through 50 millimeters of steel. And we actually did a 50 millimeter thick chunk of steel for Chorus, just to see how residual strains varied from 12 millimeter plate and 8 millimeter plate. Now you have a problem when you make neutron diffraction residual strain measurements. You need to know the lattice spacing of the unstrained lattice. And that's not so simple to do. But one way that sort of works is you can cut a little section off. This is a 2 millimeter thick slice across one of the welds. And one of the things to note here, by the way, is these are made by Chorus in the laboratory, these welds, and they actually have a very poor profile. But in fact, this is quite indicative of reality. And if you go and look at welded structures, you'll find the weld profiles are not super wonderful. And this is sort of the point that Morris again made yesterday in connection with adhesive joints. We tend to model perfection, and they tend to make rubbish. And so the two things diverge, and that's another problem with predictive capability. But what we're interested in is we then can electro-discharge machine these little teeth in it. And the idea is that we've got a thin slice, we've got separate teeth. If you measure along these teeth right at the end, in principle, you should have a residual stress-free piece of material. And we're trying to identify how the strain-free lattice spacing varies from the parent plate to the fusion zone. And these yellow lines roughly indicate the fusion zone on that specimen. And I had originally hoped that there wouldn't be too much variation in the D0, the strain-free lattice spacing in each weld. It turned out that was utterly untrue. And as you can see here, these are the corrections to the parent plate D0 microstrain in the various weld conditions. And they range from a correction of plus 875 microstrain to minus 220 microstrain. So this becomes very important to take account of. But the simple thing is you only need two values of D0. Sometimes you get a variation across the weld. But in steel it looked as though you get away with two values, one in the fusion zone, one in the parent plate. So once you've got this, you can then correct the data. This, by the way, looks quite reasonable because the undermatched had different alloying elements. And when you looked at it, you'd have substitutional alloying here, and that should be a larger strain than it is. So what you can then do is you can superimpose your residual strain profile along with the micro hardness profile on a macrograph of the weld and start trying to interpret what the data is doing. And so the yellow data here is microstrain. This sort of, I don't know, blue purpley thing is micro hardness, and these are scaled correctly according to the macrograph of the weld, and so that toe reflects these gradients in that data. And this is roughly for the 1 millimeter line, and that is for mid-depth. So you can then start going through this in some nauseous detail to try and identify trends and parameters that work. And this is the work that was done by Matteo Bozzi in a rather good undergraduate project that he did at the University of Plymouth. And as I say, you can see that the data do vary rather a lot from weld to weld. So we've got the residual strain, we've got the micro hardness, now I need the fatigue line. So I've used specimens 300 millimeters long, 40 mils wide on that assumption, 4-point bend, R.2. I've measured hotspot strain by a series of strain gauges on the surface, and I'm happy to note that the sizes were about 0.5 millimeter. They correspond with what Morris said they should, so I'm reasonably sure it's okay. We've obtained stabilized stress-strain hysteresis loops at each nominal stress value used below to get this. Now the thought that crossed my mind this morning, I remember the reason why, is it would have been nice to have measured the residual strain on stabilized specimens, although when we've done work on what fatigue loading does to specimens, there is no plateau in the residual stress. It actually just keeps steadily decreasing as far as we can tell, as long as you're prepared to fatigue cycle with things. But you still end up with high levels of residual stress. But I would not have been able to test those plates. They're actually very deformed as welded. And so you have a problem that you're going to load them unevenly, and therefore you're going to end up with residual stresses in the plate that represent the loading of fatigue you've done and not the original weld, I suspect. So I figured it was better to deal with the as-welded residual stresses rather than try and load a deformed plate that would, do strange things to the stress field. So this is how we've done the hotspot strain measurements. There's the strain gauge, there's the weld. This is the sort of data you can get. Again, we don't have enough points close to the weld to really extrapolate this terribly well, but we have done a little bit of FE work that indicates that it's at least reasonable. And you can then get out the hotspot strain fatigue performance. And these things get rather busy, so I split them out into undermatched, matched, and overmatched. But you can see there are a variety of different slopes here. So the data is quite scattered. And you can say that if you're using undermatched filler metal, 3 kilojoules per millimeter generally gives better life, particularly long lives. Again, high heat input better there, but interesting with the overmatched, the low heat input gives better performance. And so it's hard to draw generalized rules out of this. But this is what I'm interested in. I'm interested in the fatigue ranking at 10 to the 5 cycles and 2 million cycles. And so I now have a ranking of the performance of these various wells. And it is different at those two lines. And if you consider a single parameter like hardness gradient, you don't get terribly far. These are hardness gradients against well conditions. And it's difficult to make sense of that. Your 12 plate and the low heat input give the 3 highest gradients at 1 millimeter, but the 3 highest mid-depth gradients come elsewhere. So as I say, what we've looked at is a wide range of how best to describe this. Changing gradient at the weld toe, range of hardness and strain at the weld toe, and gradients at the weld toe. And what I'm presenting this morning to save time is just what worked the best. So for 10 to the 5 cycles, we actually were fairly successful in predicting the fatigue ranking of these wells, which I think is a very positive sign, I must be honest. For 2 million cycles, we weren't so successful for some reasons that I have insight into, I think. So the most successful procedure takes the maximum range of weld toe residual strain at 1 millimeter depth, which is reasonable. You might expect that to affect crack initiation, early crack growth fairly well. And you can use that as a discriminator of behavior into 3 categories. So we've plotted here residual strain range at 1 millimeter against weld condition in the same ranking order for 10 to 5 that it should be. And you get a bunch of data up there, a bunch of data there, and some below. And if you take those 3 data ranges, you can then plot them against maximum range of hardness at mid-depth, and you get 3 linear relationships, along with 1 or 2 flyers that we can't predict easily. But you can then predict the ranking from strain and micro-hardness data for 10 out of the 12 wells at a life of 100,000 cycles. And you've seen how scattered this data is. So my suspicion is that this is probably a reasonably fruitful way to try and understand how to take account of microstructural influences and residual stress influences that arise from welding. So essentially you can then relate the hotspot strain to that. So you can predict the hotspot strain from these relationships. But it doesn't work so well for the 2 welds at the extremes. And so that's sort of what you get. It's okay. I mean, you can fiddle this data 1,000 ways if you want to. But to get any sense at all out of this, I think, is positive. So when you try and put a physical rationale for these relationships, you can't, with the data set we have, get a full rationale, but you can say, well, it seems reasonable that the influence of the near toe residual strain on mean stress, and hence plastic deformation of the weld toe, is important. But control of crack growth in this low life regime, where early crack growth is relatively limited as a percentage of fatigue life, could be by bulk hardness properties rather than near surface properties. And that's why you need the mid-depth hardness range as well. But that, I think, is reasonably successful. When you come to 2 million cycles, it's less successful. You can get linear correlations in the data, e.g. hotspot strain versus weld tensile strength, which will give you these correlations for 12 out of 12 welds. What we can't do is identify a second discriminating parameter that will allow us to predict which line the data should lie on. Now, it is possible that residual stress would work better than residual strain here, but that would require more measurements. But that's a quite likely supposition. It is also possible that we would need more data in the long life regime to establish the slopes of those things better. Because I think below about 1 million cycles, I'm reasonably confident I've got the slope fairly accurately. In the long life regime, I'm less confident that we've got the slope of the fatigue performance accurately. There's not enough data in that. So either the fatigue data is not accurate enough, or probably residual stress will work better. But we have half of the result. We can at least put all the data onto a series of straight lines, and we need another discriminating parameter to sort it out. So, pretty much on time. My conclusions are that residual transverse strain and micro-hardness profiles, and you could say stress strain there instead of strain, can be used to predict the hotspot strain fatigue ranking for MIG welds made in this roller quench and temp 7-1 steel under different conditions. As I say, we've used 2 thicknesses, 2 heat inputs, 3 filler metals, and we get the fatigue ranking for 10 out of 12 welds at 10 to the 5 cycles. And while we're less successful at 2 million, we do get linear relationships, e.g. between hotspot strain and tensile strength. But I need a discriminator to work out between those. But I believe that if we are going to get to what we want to do, which is not just have a continuum mechanics model, but have a continuum mechanics model underpinned by microstructural and fabrication information, then we need to somehow build these predictive relationships into our continuum mechanics models. And then in principle, we should be able to predict the life for a particular weld in a particular steel better. Thank you.